These are the answers you should have gotten when you were doing neon and sodium, vanadium, and arsenic. So neon went all the way to the 6th p position. Sodium, we went all the way to exactly what we had before, but then sodium starts the 3 S's and he just has the 1. Vanadium, make sure you're paying very close attention. The D's drop that orbital level. And then it comes back up. It's a weird energetics thing with those two being very close together. So we were all the way to D4S2, and make sure you say it's 3D3. And then lastly, it filled all of the D's. And then we have 1, 2, 3 P's that are getting filled right over there. So if you're starting to get tired of writing things, well, there are a few different notations that you can use to write things. First of all, if you want to understand what all the electrons are doing, we can go up and we can use orbital notation. So we're going to jump up to the top again. We're just going to do it for a few of them because it takes a little while. Instead of using squares, I'm just going to use lines, but you can use either one. So for example, this would be like that. And this one would be like this. And again, if you want it to be a square, you can turn it into a square. This would be 1s2, 2s1. And again, you can turn them into squares. We can jump over and do this one over here. You can do them all. 1s2, 2s2, 2p6, and I didn't leave enough room for my 3s. Maybe I'll slide this up. 3s. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and then 1. And again, if you want those to be boxes, you can make them boxes. This is going to be really useful. Looking at it with this notation is going to be useful to see something weird that happens in one little section of the D block. There's an unusual thing that happens because this is chemistry, and of course unusual things happen when we make predictions. So this is called orbital notation. You want to be able to recognize it. This is the same thing as saying 1s2, 2s2, 2p6, and 3s1. Then we have our electron configuration. If you want to shorten this so you don't have to do so much work, we have something called the noble gas electron configuration. And you'll see that this section right here fills you all the way to this position. And so what you can do is just say, I know what the noble gas is, I just don't feel like writing it out. And so I'm going to put a bracket around the noble gas. So for sodium, this is where sodium is. So his closest noble gas, it's one level back at the end. So one level back, this is his closest noble gas, so is neon. And yes, that is neon's configuration. We did it earlier. It's up here, neon. So we did neon's configuration, but we can just write neon in. So that saves a lot of time. So if we go back to vanadium and arsenic, we can change them into the noble gas configuration. So let's see, our last place is right here. So we want to go back to the next closest noble gas. It has to be that level back. It's this one. So this is argon. And this much of the configuration is argon. And then we can just write 4s2, 3d3. Isn't that so much simpler? Same thing for him. If we're over here, the next closest noble gas is right there. And again, that's argon. And then we can do 4s2, 3d10, 4p3. But again, at least we got out of having to write all of these out too. Something else, you can see that we have some different coloring designations going on. So this goes back to the idea of what is a valence electron. So the valence electrons are not always at the very end. The valence electrons are the electrons in that outermost energy level. So it gets pretty easy to spot them if we go back up here. So hydrogen, this is a valence electron because he only has that electron. So with those ones. So let me use that same coloring. It used orange. And actually, I'm going to use it over here. So the valence electrons are the orange ones. And that's because there's only an electron in that orbital. Now, it's the second energy electrons. Those are the valence. And then these ones, these are lower energy levels, so that's the core electrons. Again, that's a core electrons. And then these are all in the second energy level, so it has 5 valence electrons. The reason we care is because the valence electrons are the ones doing the chemistry. And I mean like all the chemistry. It's all those valence electrons that are doing it. Let's keep looking. So our core electrons, so that's the first energy level, that's a core electron. And then those are the valence, so that has 8 valence electrons. Now let's look what happened over here. Now we have a new energy level, so there's only 1 valence electron. Everything else is core. So that's core, 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 and core electrons. So here, look for the largest number. Here's the largest number. That's the valence electron count. Now, this one's a little funny, so I'm going to make a little addendum with this one. So purists in some fields will say this is the only valence number of electrons. But other people, including the OpenStax textbook and what we're teaching, will include, remember how like really these guys are really, really close to each other? They'll include these as those valence electrons. So if you end on a 4s and it has a 3d, it only is like, or like a 5s and it has a 4d, the d's that are right in there can be considered valence electrons. And again, that's only like when you're in this section right here. It changes and it goes back to normal. This only has 5 valence electrons. And in this case, these guys are the core electrons, including him. So the only time that the whole go with the largest energy level, and that's your valence number of electrons, doesn't work is when you're ending with a 3d or a 4d or a 5d. And then you have to include them with this valence electron. You're going to see what's going to happen with those electrons in just a minute.